Okay, let's continue. This is going to be part 29 for General Chemistry 141. We are stopped at the middle of the reduction oxidation reaction and introduced the role play of reactants. We finished that. Now I rewrote it and then into a little bit clearer fashion. So what happens for these reactants, right? The reactants right here. What kind of role they play? The magnesium, right, loses electron to become a magnesium 2 plus cation. So lose electron to be what? Lose electron is going to be oxidized, right? And then become what? Become a reducing agent to deliver its own electron to something else, which in this case is the oxygen atoms. Gain electron from magnesium to be what? To be reduced. And at the same time, because it is being reduced, it becomes a oxidizing agent. Oxidizing who? Oxidizing the magnesium. So they have a kind of relationship. I become this and do that to you, and you do that to me and become that. You know, that's the situation. Now, but this kind of situation we have to emphasize here, right here. Now, the both oxidation states for the magnesium and oxygen atom were changed before and after the reaction, right? Now, before they have a certain value, after they have different value. Now, that is true, but what caused this to happen is the electron being transferred hand to hand, right? So what is the timing for the electron being transferred for this to happen, for the reaction to go forward to completion? The time is different. Most of people did not understand. They teach this kind of concept, say, okay, you check the oxidation state for the species in the redox reaction, find if they are different before and after the reaction, right? They change their value for the oxidation states, or the oxidation number change for magnesium or oxygen, whichever you talk about. And then the electron transferred between the magnesium and oxygen, and is between the reactants and the products. Now that is totally wrong. Now I have to emphasize this. This is totally wrong. So what the important thing is, I put here as the important final note for the redox reaction. That is kind of like I try to persuade everybody in my class learning chemistry, because chemistry involves atoms. Atoms, ions in the compound, they are so small. They are invisible, right? So if they are invisible, you cannot visualize it. Visualize is not possible, so you have to imagine. So I said, close your eye and imagine. Imagine what? Imagine there's a beaker, there's a solution, or this and that, and then they are so small, become dissolved, dissociate, and then colliding with each other, and then have a reaction, interaction, and we call it reaction, and occur, and then they exchange partner, or do this and do that, and something, and there's some kind of driving force, and what kind of compound will be generated and become gas or become solid, right? And then they complete the reaction, and something will be not that lucky, right? It remain the solution as spectator, those and that, and these we have to imagine them, right? So imagine this: if the reactants in the redox reaction, right, they change the oxidation states before and after the reaction, between the reactants and the products, of course, they change. Then they involve the electron transfer. But electron transfer, when that occurs, that's critical. The electron transfer in redox reaction, the electron transfer process only occurs between what? Between the reactants. And it has nothing to do with any of the products. Why? Because imagine this. I'm reactant A, you are reactant B. And I'm supposed to reduce you to be oxidized myself and then give my electron to you. Now, before I give my electron to you, I'm me, you are you. Now, after I give off my electron, I'm no longer myself and become something else. And you gain my electron and you become something else, not yourself originally. So when electron transferred between you and me, hand to hand, that very moment, both of us no longer exist as reactants, become the product. But only very short period of time that happens, right? Electron transfers were very quick. And then during that process, we no longer exist as reactants. The new products, soon after that, at same very moment, soon after that electron being transferred, and you and I disappear, and the new products will be generated. That is the process. Now, so that's why we have to put timing concept in there. The electron transfer will only occur between the reactants, you and me, right? Soon after we gain or lose electron, both happen to both of us, and we no longer exist. We become a new product. So, will electron transfer has anything to do with the products? No. Before the products, moment ago, maybe 1 picoseconds or some earlier, then the products will be generated. We are the reactants. But during that picoseconds or less, then we transfer the electron. That process during that we still consider ourselves as reactants, not relate to any products. You follow me? So that's the point. So in other words, the very moment electron transferred hand to hand between the reactants no longer exist. And then the new compounds or species, right, could be elemental, like a metal elemental, a species, are produced as products. Also, this process also occurred at that very moment. It's just slightly slower behind, right? So that's how we have a clear cut for timing. Electron transfer only occur between the reactants, not the products. If you write down, it takes you time, right? Do you have to spend some time to write a chemical reaction equation from left to right? Yeah, that's the same thing. If you understand this way, do you have to write the reactants first and then write the products? So that timing, when you're writing the time, the reactants both appear on the paper on the board. That's the time the electron being transferred, and then you write down the products. Now, does it mean the same thing? The transfer of electron has nothing to do with products. Is that similar? If you don't understand it, try to close your eye and think a moment. You will get it. Okay, so that's quite important. All right, now we repeat this. Now, I will give you another example, right? Because why? We have to give you another example because we try to let you to understand the spectator as well as the new fashion of balance equation with what? With electrons, but not just counting electrons. We're going to split the chemical reaction, redox chemical reaction, into 2 half reaction equations. And then we introduce that when we introduce the net ion equation and ion equation. After that, we're going to finish this whole section called redox reactions. Alright, so let's give you another example. Alright, this example is quite simple, but will give you more to deal with the concept we are concerned. Right? Here, we're going to have a solution. It's a dilute solution called, of hydrochloric acid, right? And then we're gonna react the acid with solid magnesium zinc. Now that it's kind of a metal, right? It's an elemental species, and then see what happens, right? See what happens. Now, so example again. Say if a pinch of magnesium zinc metal, right? Symbol Z and solid. Of course, the oxidation state 0, right, is dropped into, right, dilute hydrochloric acid. Of course, it's going to be aqueous, right? Right, that is the process, right? What happens? So you have two reactants. One is solid metal, zinc. Another is dilute aqueous hydrochloric acid, right? So the equation, of course, the reaction equation, right? Reaction equation, right? So it's going to be the zinc, right? The zinc started, all right? We don't put arrow because that was started for it. It's not produced, right? It's not produced as product. So we react with hydrochloric acid, aqueous, right? It's not smoking hydrochloric acid is concentrated, right? 12 moles. It's diluted with water. All right, now I leave some space in front so that we may need to put a coefficient as we balance equations, right? And then that is a single displacement or single replacement reaction. So let me just put down there S stands single displacement SD, right? Go in one direction, irreversible, and what happens is the zinc replaces the hydrogen atom, right, in the hydrochloric acid, and to make a zinc chloride, and then the hydrogen will be released as gas molecule out of the solution. Right? That is fact. So yours actually the solution is colorless, right? And zinc is a gray, dull-looking metal, small pieces, right? And then you drop in there, and then immediately you see bubbles. What is the bubble? The bubble is hydrogen gas, diatomic molecule. Bubbles out of the solution because less dense, so bubbles out, evolve into the air, and can no longer go back in the solution, go that way, so it is irreversible, right? So the product zinc chloride, right? I'll put subscript down there, you tell me, right? And then it's aqueous, right? It's like a zinc dissolved in there. And then you have the hydrogen gas, right? Of course, we already said it's going to come out, right? Now, as we know, zinc is 0 here, right? It's an elemental metal, right? 0. Hydrochloric acid, hydrogen is +1, right? It's +1 here, and this is -1 for chloride, right? Now, come to this side as products. Now we do that. It's a fact between reactant and products. We try to find the difference of the oxidation states, right? Or the oxidation number, whatever you call it, both the same, right? In this case, again, it's 0 because it's diatomic monoelemental molecule. One element involved. They are exactly the same. We did it. We don't want to repeat this. Spend time, right? So that's 0. Now, but here, chloride is a halogen, right? And either +7 or -1. Most of the cases -1, right? We already talked about the trend, the periodicity trend of oxidation states on the periodic table. We talked about it a long time ago. Now we applied it. That's -1. +7 is not possible because this is going to be cation. Because why is cation? Because zinc's metal, right? Metal don't form anion, right? Don't form anion. It's going to be cation. So cation and cation is not possible because it should be a neutral 0 compound, right? Binary compound. 2 elements, right? Binary compound, right? So this was also, we mentioned that, right? That's number 30, right? Number 30. It's the last one on the third period, all right? The third period is a 3D electron involved. And that is zinc, it's number 30, and it has only one particular oxidation state. Its value is +2. No other choice. So this one's +2. This one is +2. Now this is -1. So do we have to multiply 2 to give you -2 to achieve the neutrality of this binary compound? Of course, yes. So if you multiply 2, then we have to put the subscript down there for the chloride. The chlorine become 2, right? So now, seems to be everything is in place, and the molecular or ionic compound formula are exactly correct, right? Correct. Now we are able to find out the old-fashioned way to balance chemical reaction equation. Our zinc is going first because you talk metal. Now, we're not going to spend time on balance equation because I already gave you a handout, and then we've been doing chemical reaction balancing, right? So far, almost every example we did that, right? And some kind of tips we apply, right? Whatever out of the 12. All right, so zinc goes first, metal, zinc, one, that's balanced, right? And then after zinc, we balance what? We balance hydrogen, right? Hydrogen. If we don't have metal, we balance hydrogen. Did I mention that in my handout? So in this case, the zinc is balanced and the hydrogen is next. Here I got 1 hydrogen, right? Here are 2. So we definitely have to double this, right? We double this, right? Double it. Now if we, after double this, become 2 hydrogen and then 2 chlorine, right? 2 chlorine. Then zinc chloride got 2 chlorine, so chlorine is balanced. Now hydrogen, so the whole thing is balanced, correct? It's balanced. Now because it is a reaction occurring in aqueous solution, right? And it involves almost like a 3 out of 4 physical state except what? Except liquid, right? Solid, gas, and aqueous, correct? So if it's aqueous, we believe those substances or species in the aqueous physical state means they are a ionic compound of some kind of ionic compound, right? And they were able to dissolve and dissociate and ionize in the solvent as water. And if they are strong electrolytes, of course, both were strong electrolytes, they will be 100% dissociated, right? So we are able to, this is a reaction equation and this is balanced also, right? So the second step is writing a complete ionic reaction. So just put ionic equation. Complete ionic equation, right? Complete ionic equation, right? So if we want to write a complete ionic equation, we already did one on last in one last part, right? So you have to find out which one is complete dissociated, which is this one and this one, these two, right? Solid, stay solid before they drop in, right? And after reacted, they no longer solid, become cation right here. So here you have to copy the zinc because that's where you start with, zinc metal solid, correct? You may have to remind yourself with a 0 oxidation state on top of it. But then here, you got 2 HCl, which means you have hydrogen, cation, and the chloride anion, but you have 2 of them. So you have 2 hydrogen, if they dissociate, become aqueous, 2 proton, right? And actually, they're going to combine with what? Combine with the water, become a hydronium, right? H3O 1 plus. But here we simplify it. And then that is from this, and then you have 2 chloride. So you have 2 chloride, 1 minus each, also aqueous, right? That's all. That's all for the reactants. One stay as solid, another one dissociate 100% completely, become 2 pairs of cation anions, right? 2 cation anion pairs. So then we go single displacement reaction direction going that way. Now the zinc chloride, the zinc instead of solid become part of the ionic compound as cation and then lose 2 electrons because 2 plus, right? So zinc, right, is going to be in aqueous solution with a 2 plus charge as cation, not plus 2, plus is oxidation state. When they dissociate into cation, we say 2 plus, not plus 2, right? Go away, and then you have what? You have chlorine, chloride, how many? Subscript, don't forget, so you have 2 chloride, right? Is what? 1 minus each, and its physical state is aqueous. Because this whole thing dissociates into these 3. That's 3 entities. 2 are identical chloride and 1 zinc cation. Now you have to have, that's 3 units, right? 3 different ions, right? Alright, so then this is what? Add this hydrogen gas, right? It's diatomic molecule, and soon after it was generated, it will be bubbled out. I said when you drop zinc into the almost colorless dilute hydrochloric acid, and then you see bubble immediately. Soon after zinc go into the solution, you see the bubble come to covers every small piece of zinc on this molecule zinc, and then if you shake a little bit, it just keep on bubbling very, very violently, and then they all get out into the air, into the lab. So that's hydrogen gas. It is not going to stay inside the solution, so it is come out. Stay still, come out. Now, so that is a complete ionic equation, because why? Anything we are able to dissociate, ionize it, which is this one, that one, we done it. Right? So they become cation and anion pairs. Now, look into this. Now, do we find anything exactly identical on either side as reactants and products, so that we are able to consider them as what? As spectator, right? As spectator, which are not actually participate in the reaction, but it's an onlooker. They are an onlooker looking whatever happening in front of their eyes, but in the same room, right? Same beaker, right? It's supposed to be exactly the same. Is the zinc here and the zinc, they're the same, right? Zinc? But they are not same. Why? There's 3 things. One is the oxidation state. Here's 0, here's +2. We call ion charge 2 plus. The other one is what? One solid before the reaction occurs. After the reaction occurs, it no longer solid. It is dissolved in the water, or dissolved in solution in the water solvent, right? And then reacted and lose electron, right? Lose electron to somebody, become cation, become what? Oxidized. This one become oxidized and to the zinc 2 plus. So they are no longer same species. Aqueous solid 2 plus 0. So they are not identical. They are the real participant as reactant and the participant of reaction as products. Is that clear? Let's check the hydrogen. Hydrogen on the left is in the hydrochloric acid. It's a strong electrolyte and then completely dissociate and ionize into a pair of 2 pairs of cation and anion, right? And there's a 2H1 plus aqueous, but on the other side, they're both H, right? No, they are both hydrogen atoms, but this 2 hydrogen atoms become a diatomic molecule. These are 2 hydrogen atoms losing electron each, become proton, right? So they are no longer the same. One is aqueous in the solution. This is going to come out as gas. See that G down there? Right? G down there. So they are no longer the same identical species. They are not spectator. They are the real participants of the reaction. One on the left as reactant, and the one on the right as products. Is that clear? So it's clear. Now let's look at chloride. The chloride coming out from the hydrochloric acid, right? And there is 1 minus charged anion, but 2 of them. Aqueous solution's physical state. And here we got the products, which is also zinc chloride. This is what? Hydrogen chloride gas, and become acid, which is hydrochloric acid. Change the naming system a little bit. IDE become IC, right? That's if you learn the nomenclature, and you should remember that. And then, but these 2 anion exactly same. This one, 2 of them. 2 chloride, 1 minus 2 chloride, and aqueous. So these 2, they are exactly same species. So they are what? They are the spectator. We are able to cancel out on both ends, or both sides of the equal sign. Now the leftover is what? The spectator, right? Let's say spectator. In this case, only one spectator is what? It is two of them, chloride and ion in aqueous physical state. Is that clear? All right, in physical state, let me make it a little better. All right, that's the spectator. Now, what is the leftover? We call what? The leftover we are going to call is another term called net ion equation. CE. The net ionic equation, shorthanded. All right, shorthanded. So what is left over? Net ionic equation will be the zinc left over, solid, add, right, 2 protons, that's a 0 charged, it's aqueous, and then become what? Become zinc, aqueous, 2 plus, and hydrogen gas, 0, as oxidation state. Now that is the net ion equation. Net ion equation. These two are the same from zinc, but they are no longer same species. We call species including substance, compound, ions, atoms, molecules, everything we in general call species, because they have too many different features to describe individually, so we call them species. All right. Now this one is net ion equation, but what happened to their oxidation state being altered? Because electron transfer. Electron transfer are said between what? The reactants, right? Between reactants. So they start from here, right? So the next subject is going to be the electron transfer. Process, electron transfer process. So how many electrons? All right. The electron, 2 electrons from one zinc, right, goes to where? 2 electrons lost, right? 2 electrons lost to what? 2 electrons go to 2 protons. So let's see, electron transfer. Let me just draw a picture. In the past we did it. Let's make this. So how many electrons? 2 electrons, apostrophe S, right? 1 minus charge, electron, 1 minus charge, right? So where it goes? Go from zinc. This is 0. Let's make sure this is clear. 0. Lose 2 electrons. So zinc being what? Oxidized. Proton being reduced. The 2 electron goes into that. Now what happened? After zinc lose 2 electrons, become zinc 2 plus, and the 2 plus 1 plus charge cation of hydrogen gain 2 electrons each, right? And then 2 of them, one get 1 electron, 2 of them become a 0 charge. So this is the transfer process between these two. Now, is that clear? And after this reaction, after this transfer process, is the moment after this transfer process just finished, no longer exists. These two no longer there, become these two. You see my point? Right here, we just talked about final important notes, right? Final notes about this. At the very moment they become this, these no longer exist, they become that, right? Now this kind of net ion equation involve electron, can we also cut them in half? It's called half reaction equation. That's EF. Half reaction equation. Half reaction equations. Now we're going to indicate what kind of processing involved. The zinc says lose 2 electrons. So lose is subtract, right? So we start from where the reaction starts. Zinc, metal, lose 2 electrons. Lose 2 electrons. And then give you what? The time's all up, and then we continue after this, and then give you zinc,